This video is on exponential growth models. And we're going to start off just by developing, kind of where we get the general formula from that we use for exponential growth. And then we'll do some applied examples. This formula actually would also be used for decay. There's just one small difference in it. But just taking a look at a quick example here. Suppose I had f of x equals 2e to the 5x power. If I was to take the derivative of that, f prime of x, remember how you take the derivative here of an exponential, right? So you have a constant times a function, the constant 2 will stay in front. The derivative of e to the 5x, remember how that works. It's really the chain rule on e, so you want to keep what you see. So, it's the derivative of the outside is e to the 5x, so keep what you see, times the derivative of the inside, in other words, the exponent here, so times 5, right? So derivatives of e, you keep what you see, multiply by the derivative of the exponent, so times 5. Now, the thing to notice here is that if I have 2e to the 5x, that's actually originally what f of x was. So another way of writing what f prime of x is I could write it f prime of x equals, I could really just call this f of x times 5, or f prime of x equals 5 f of x. So we're writing it in terms of the original function f of x. Now this happens with exponentials, right, because of the fact that when you take the derivative of e, you get itself, and then you're just multiplying by whatever the derivative of the exponent is. In general, right, so in general, y equals ce to the kx is the only function whose derivative is a constant times itself. In other words, y prime is going to be equal to some constant k times the original function y. In this case, looking at what we had here, right, if we have y equals ce to the kx, we had, y is equal to 2e to the 5x. So our k is 5, right? So when you take the derivative of this, right, we ended up with 5 times the original f of x. That's k times y here, k times the original function. F of x is the original function, that's the y. So, this is the reason why it works out the way it does on the left. This is kind of the general way of describing it, but it kind of allows us to generalize this. If we saw something of this form, we can work backwards to get something of the original function form, right? Y equals ce to the kx. So we have a theorem that we're going to refer to here and use throughout the section. The theorem says y equals f of x satisfies dy over dx equals k times y, which is really the same thing as this says, all right? So, or f prime of x equals k times f of x if and only if, what it's really saying is if and only if the original function has the form we just talked about, the y equals ce to the kx power for this first form of it, or f of x equals ce to the kx power if you're talking about f prime being the derivative. So basically what we're saying is that if you know the derivative has this form, right? So the derivative is equal to a constant times the original function. The derivative is equal to a constant times the original function. then you know that the original function, right, that's what we mean when y equals fx satisfies it. We know what the original function has to have in terms of a form. It has to be the function, in this case y for the first part, is equal to some constant c times e to the k. We pick k right out of there, x power. If the function was called f of x, we say f of x equals. But these, you know, this left side means the same thing as this right side. We're just using y here, we're using f of x here. So, for example, if I said, given dA dt, so derivative of a with respect to t is equal to 3a. Find the general form that satisfies the equation. We talk about here, you know, in calculus, we really call these differential equations. But, you know, for the way we're looking at it, we're saying the derivative is equal to 3a. So, this derivative with respect to t is equal to some constant 3 times the original function a. This tells us that we have the form we need to apply what we just talked about in the theorem. In other words, right, the theorem said, you know, y prime equals k times y, or dy dx equals k times y, right? So in this case, you know, y is like a, x is like t, and then k is 3, and then y is a, right? Because remember, these have to be the same, right? The derivative of a with respect to t, and I'm using it in terms of a. So I know my original function name is whatever y was, in this case it's a. So a of, because it's a derivative with respect to t, I'm going to call it a of t. Alright, just like, you know, we could say this is f of x or y of x here. This is a of t. It's equal to, c is a constant we don't know, right? That's why we call this the general form. So it's equal to c times e to the k. You know what k is. K is whatever was being multiplied to a in front here. So k is 3. And then make sure you use not x, but we're using t because t was the variable we had, right? So this is y, this is x, so in this case it's a and t. Just following the same form. So a of t equals c times e to the 3t power is the general form of the equation that satisfies this differential equation. In other words, if I took the derivative of this, it would be equal to that. We don't know what c is, right? The reason we don't know what c is because, you know, even going back up here, you can see it, the constant is buried within the function, right? So we don't know what c is. Now there's ways of finding that, and we'll talk about that in a little bit. But understanding if you have this equation, this differential equation, right, the derivative is equal to a constant times the original, you always can write the general form in this way. We'll do just one more that's similar. If I said, for example, given dp over dt equals k times p, you know, and I said find the general form. That satisfies the equation. Well, what's the name of our y value? What's the name of our function, in other words? Well, it's whatever's in the top part of our, right, derivative with respect, derivative of p with respect to t. So the name of the function is p. It's p of what variable? Well, t is like our x value, so it's p of t is equal to, because we have k times p, right? This is our k. Since we have k times whatever the y value was, right, or k times whatever the original function is, I can write this as c e to the, now k is k, right? So k t power. In the previous one, right, we knew k was 3, but if we don't know what it is, we're just going to call it k still. So it's the general form. We use these for exponential growth and decay problems. So I'll introduce it here, and then we'll do some applications. So for exponential growth / decay models, because you really do use this for both, and I'll kind of explain the difference between the two as you do it. Alright, they use the differential equation dp over dt, meaning the derivative of p with respect to t is equal to k times p. Or another way of saying that same thing is saying p prime of t, right? That's what derivative of p with respect to t means. It means p prime of t equals k times p. So one is in the Leibniz notation and the other is in our more traditional notation. Alright, so exponential growth and decay models use this differential equation here. If k is greater than 0, we know that it's going to be exponential growth. So if k is positive, right, if k is greater than 0, we know it's exponential growth. And if k is less than 0, right, you see a negative value there, right, for k, then we know we have exponential decay. Right, so they use these models, and then they have a solution. Right, so they have solutions of the form p of t equals, now we just saw it on the previous page, right? So we know the name of the function is p, so it's p of t, some constant c times e to the k t power, right? So it's what we just looked at. So they have solutions of the form this, and you know, something to point out, if I was to sub in t equals 0, right? So you know, a lot of times when we do these problems, we're talking about when t is equal to a time. If time was 0, what's p of 0? Well, p of 0, that's equal to, if I substitute into here, right, it's c e to the k times 0, because I'm subbing in for t. Well, that would just be p of 0 is equal to c times, well, e to the 0 power, that's just going to be 1, so c times 1. So we end up with p of 0 equals c. So what I want to point out here, because this is the way you're going to see it more often, and you may have seen it this way before, is we denote c as p sub 0 to represent the initial amount. Because when t equals 0, right, that'll be the initial amount. We call it p of 0, but just to note this in here, instead of calling it c, we're going to call it p sub 0. It's going to be the same thing though. So it's the same formula. We just use it as p of t equals p sub 0 e to the kt, indicating that p sub 0 is the initial amount of whatever we have that's growing or decaying. You know, sometimes it's money, sometimes it's a radioactive substance, sometimes it's a population. It could be anything that's growing or decaying exponentially. So when you see this variable typically will match the variable that we used for y, but this p sub 0 means the original amount present, the initial amount. All right, and we've seen this before when we talked about compound interest formulas, right? So we want to use, all right, so we use this to find the amount in an account with interest compounded continuously. Right, this is something that we talked about earlier. This was the formula. It was called A, or A of t equals this, but it's the same idea, right? P of t is just the name of it. P sub 0 is the initial amount present. Instead of calling this K, we called it R for the interest rate, but K is just the same thing. It's going to be the exponential growth rate. And, you know, we've used this before. So just one quick note, and then we'll do some examples using it again. All right, so note when we talk about K, it's either the growth or, right, so growth or decay rate. Positive means growth, negative means decay. So K is the growth or decay rate. You know, here call the growth or decay constant, means the same thing. So let's take a look at some examples here. If you're in my class, you have access to this, you know, as an attachment. But these are exponential growth examples we're going to look at. So it says, suppose an initial amount P sub 0 is invested into a savings account in which interest is compounded continuously. That's important. At 7% per year. That is, the balance grows at a rate given by this differential equation. So derivative of P with respect to T is equal to 0.07 P. And they want us to find a function that satisfies this equation. So first off, you should recognize this is the form we've been talking about. Right? So this derivative of P with respect to T is the same as what we had on the previous page. Like P prime is equal to 0.07 times P. So this 0.07 is like our K that we were talking about earlier. And the other thing that you want to notice is that where it comes from, the 7% per year, that is your 0.07 that they're using in this formula. They're just telling it to you in the problem, and they're showing it here. So we know that the function has to have the form that we just spoke of. So this is, what's the name of the function? The name of the function is P, because derivative of P with respect to what variable? T, so it's P of T, equals some constant C, which we said we're going to call P sub 0 for the initial amount, all right, times e to the kt. Well, what's k? K is whatever was in front of our P here, so to the 0.07, all right, and then times t, because t is our variable. If that was x, you'd put x there. And this is, you know, the general function that would satisfy this differential equation. There's really not a lot to it. It's just recognizing the form. Now, if I didn't even tell you this, you should know that when interest is compounded continuously, right, we have this formula. You remember from earlier, probably, that it was the amount was equal to P0 or P e to the RT power. Well, R would be your interest rate. In this case, we're just calling that K. And notice that the 0.07 is positive because it is a growth. The next part says, suppose $100 was initially invested. Find the balance in the account after 2 years. So suppose $100 was initially invested, so that's telling you what P0 should be. We want to find the balance in the account after 2 years. That's telling you what T should be. So we're looking for P of 2, in other words, right? The amount in the account after 2 years. So it'll be called P of 2. It's equal to P0, which is 100 now. They were telling us what the initial amount was 100. E to the 0.07 times 2 power. And this is something we've done before. You should know how to calculate this. On your calculator, right, if we had 100 times e to the 0.07 times 2, make sure that 0.07 times 2 is both in the parentheses on that exponent. We hit enter, we got 115.027. I'll round that up since it's money to 0.03. So this equals 115.03, and this is in dollars. Now, if your calculator doesn't display all the operations on the screen, remember you have to multiply these exponents together first, then do e to that power, then multiply by 100 to get this answer. So after 2 years, if I initially invested $100, this is how much would be in there. Keeping in mind that if you were looking at this, right, we could change how much was initially invested, and that would change what happens in the formula. So that's why we have this general form. They're telling us some more information. We can figure out how much would be in there at a certain time t, right? Because p is really a function of t. So at any time t in the future, we should be able to determine how much would be in the account as long as I knew the initial amount. This next part says, in what period of time will it take for the initial investment of $100 to double? So think about what that means. The general formula, right, P of t would equal P0, which we now know is 100 based on what they told us, e to the 0.07t. Now if I wanted it to double, right, to double means times 2, right? So if I said triple would be times 3, quadruple would be times 4, but if I wanted to double this, really I'm saying, well, then I want to look for when the P of t, the amount in the account, becomes 200. And I'm trying to find what? In what period of time? So I'm trying to find time now. So, you know, this 200 here is just 2 times the 100. Make sure you know where I'm getting this from, right? The doubling time means we want 200 on this side is equal to 100 e to the 0.07t. So when I go to solve this, right, 200 is the amount in the account at some specific time t. I don't know what t is though. Make sure you're solving this in the right spot. Well, how do you solve this? First off, you have to isolate the exponential. Sometimes people try to take logs right away. Remember, this has to be isolated as an exponential before you can actually get that exponent out of there. So we're going to divide by 100 each side. If you divide by 100 each side, 200 divided by 100 gives you 2. It's equal to e to the 0.07t. And then we want to solve this. To solve this, we take natural log of each side. Take natural log of each side. We have natural log of 2 equals natural log of e to the 0.07t. Remember why we're doing this. When you take natural log of 2, let's just keep that part natural log of 2 for now to keep it exact. Natural log of e to the 0.07t. Remember the bases match here, right? So natural log is base e. You have of an exponential, which is base e. When the bases match, you just take the exponent. So we have just 0.07t, right? So natural log of e to a power is just the power. And to solve this, we divide by 0.07, divide by 0.07. So end up with t is going to be equal to ln of 2 over 0.07. Now that's the exact answer. Let's approximate it. We'll just use to the nearest tenth. So if I approximate this, t is approximately, and we can look at it on here, natural log of 2 divided by 0.07, 9.902, so approximately 9.9, and make sure you know what the units are. It says 9.9, what are we looking for? Time, so it's time was in years. So at approximately 9.9 years, right, the amount in the account will double. Now, this said the initial investment of $100 would double. This actually wouldn't matter what the initial amount is. You could actually say this for any initial amount, and to double it would still be 9.9 years. Let me show you why, because this is going to actually be easier to use, I think, overall. But suppose that I didn't know how much was in here, so I just called this P of t equals P0 e to the kt. All right, so in our case, we know k is going to be 0.07, so we would have P of t equals P0 e to the 0.07t power. If I asked you to double this, right, well, P0 is the initial amount, then the P of t would just be 2 times P0 equals P0 e to the 0.07t power, right? Because if P0 is the initial amount, 2 times that would be double it. And all we're going to do here is divide each side by P0, because I want to isolate the exponential, just like I did a minute ago. And end up with 2 equals, the P0's cancel here, right? On the left side, that's how I end up with 2. The P0's cancel here, so I'm left with 2 equals e to the 0.07t. Well, isn't that exactly what I ended up with here? So the point being is that if you don't know the initial amount, you still could find the doubling time, right? So in general, right, when you're trying to find the doubling time, right, to find doubling time, you can use as a shortcut, right? It doesn't matter what the initial amount was. If the initial amount was 1, this side would be 2, right? So that's why you could try to pretend like P0 is 1, and then the amount that's double that would be 2. You can use 2 equals e to the kt, and then solve for t. So, that's how we're going to use this to help us as a shortcut. If it said, how long would it take for initial amount to triple, you would put 3 on this side, because you'd use like your P0 is 1 and this side is 3. So it gives you a shortcut way to get there. If you feel more comfortable writing it in, you can, but they won't always give you the initial amount. So you have to understand how to find it if you don't know the initial amount, just in the general form. All right, the next example says a bank compounds interest continuously, and so it'll double your money in 12 years. What is the annual interest rate? So annual interest rate, they're actually asking you to find K. A bank compounds interest continuously. That tells you that the formula you're using is a compound interest formula. It says it'll double your money in 12 years. What is the annual interest rate? Well, double your money, right? We just kind of talked about how you find doubling time. Well, it's 2 equals e to the kt. Now they told you what's t. Remember, to solve this for k, you're going to have to know what t is. Well, 12 years is your t. So this formula is actually 2 equals e to the k times 12. And now I will try to solve this. To solve this, I need to be able to get this variable out of the exponent. So I'm going to take natural log of each side. So I end up with the natural log of 2 is equal to the natural log of e to the k times 12, is the same as writing it as 12k. And then solving here, natural log of 2 I will keep for now. Equals natural log of e to the 12k. Remember, the bases match. You just take the exponent. So natural log of e to a power is just the power, which is just 12k. And then we divide by 12 and divide by 12. So I get k is equal to, now the exact value is natural log of 2 over 12. If we were going to approximate this, right, so we divided both sides by 12 here, we want to use our calculator. So k is approximately, if I use this as natural log of 2 divided by 12, I get 0.05776. So k is approximately 0.05776. Now, they asked us to find the interest rate. Typically, we talk about that as a percent. So this is the interest rate as a decimal. As a percent, how would you change that? Well, basically, you multiply it by 100. You move the decimal place 2 to the left. So it's approximately 5.7. We'll round this up to an 8% for the interest rate. So this would be the annual interest as an approximation. Keeping in mind what the question asked us, right? So they told you double your money, but they asked us in this case to find the interest rate, to find k, given a value of t. They could also have told you what k is. They could have told you the interest rate, and they could have asked you how long would it take to double your money. Then you'd be subbing in for the k and solving for the t, kind of like what we did in the example above here. So they could ask you either type of question. And if they said triple your money, just remember this would be a 3 on this side. You could set up the general formula and solve for it that way as well. Let's take a look at just a couple more examples. So this next example says the number of immigration prosecutions, N, is growing at a rate. All right, so growing, it's positive. All right. Growing at a rate of 18.2% per year for t years after 1994. After 1994 is important, right? So t is years after 1994. And can be approximated by this function n prime of t is equal to 0.182n. So it's a differential equation, right? It's defined in terms of the original function. And it says find the function that satisfies the equation given that 6,100 prosecutions occurred in 1994. So first thing we want to look at is, what's the name of our function? Well, this function's called n, right? They tell you here, they also show you here, and the derivative is the derivative of n with respect to t. So I know I'm looking for a function called n of t, right? That's the original function before you took the derivative, in other words. Now it should be equal to, since I have this form here, we know that this is the form for an exponential function, and we know that those have the form of, usually we put p0 here. Since this is called n, I'm going to put n sub 0, right? E to the kt, right? That's the general form. And let's talk about filling in the pieces that we know. So n of t is equal to, well, what's n sub 0? It's the initial amount. Well, t is years after 1994. So if they tell you 6,100 prosecutions occurred in 1994 when t equals 0, right, they're telling you what n0 is. That's the initial amount. When t equals 0, the initial amount is 6,100. So we can sub that in right here for n0, 6,100. E to the, what's k? Well, it's 18.2% per year, but they also have right in the formula, right? It's k times n. This is k as a decimal, so 0.182, and then t stays t. Remember, this should be a function that has t in it, because it's a general function that you want to substitute t in to be able to find a number of prosecutions at a time in the future. All right, so n of t equals 6,100 e to the 0.182t. Once you have that, it says to use this, we want to estimate the total number of prosecutions in 2007. So first thing to note is that, in 2007, what is t? You can't just sub 2007 in here because t was based off of something specific. It was modeled from years after 1994. So we really need to find t equal to 2007 minus 1994 first. And if you do that, 2007 minus 1994, we get 13. So t is 13. So what they're really asking you to find is n of 13. To find n of 13, all it's saying is to plug 13 into your function here. So we have 6,100 e to the 0.182 times 13. And this equals, we can evaluate this on our calculator. If it doesn't display everything on the screen, you multiply the exponents first, then take the exponential of it, then multiply by 6,100. Doing this, I'll do it here. We've got 6,100 times, I can e to the, make sure the 0.182 times the 13 is all in the parentheses. Close the parentheses. I got 64,993.59. So think about what this means. These are immigration prosecutions. You can't have a fraction of a prosecution. So what we're going to do is we'll round that up to the nearest whole number. So this equals 64,994. And remember what we're finding. We're finding prosecutions through 2007, right? So that's what we're finding there. So that was using our formula to find the number of prosecutions. We could also use it in other ways. The next part of the question asks us, what is the doubling time for n of t? Well, doubling time, similar to how we just did it in the last question, it means how long until twice the amount of prosecutions occurred. So we have 6,100 here. Now, I'm going to keep this general. So instead of using 6,100, I'm going to say, if I want a doubling time, just to make sure you understand it, it's 2 times the initial amount. It would be equal to n0 e to the kt. All right, so what I'm really saying is the n of t here would be double whatever the initial amount was. And this is just keeping it general, just so you can see this again. And then how do I solve this? Well, I want to isolate the exponential here. So I would divide by n0 on each side, the initial amount. And they cancel here to give us just 2, equals they cancel here to give us e to the kt. Now if I'm trying to find doubling time, right, we're here. The only thing I need to do is, I'm trying to solve for time. That means I better know what k is. And we know what k is, right? It's actually given to us in the problem, the 0.182 that you can see here above. So we know that 2 is equal to e to the 0.182t. And to solve this, we take the natural log of each side. So natural log of 2 equals natural log of e to the 0.182 t. And if you understood what we did on the previous page, you could have started the problem right here. 2 equals e to the 0.182 t, because that would just assume that you're doubling the 1 to 2 here. Remember what happens here. Natural log of 2 will stay natural log of 2. Natural log of e to a power, remember, is just whatever the power is, because the bases match. And then we're going to divide both sides of this by 0.182. So we have natural log of 2 over 0.182 is equal to t. Right, that's how you would solve that. That is the exact form. We want an approximation for the doubling time, so we'll do natural log of 2 divided by 0.182. I get 3.808, so t is approximately 3.8, and we'll call this time, so it's years. So 3.8 years what though? 3.8 years after 1994, and we should have that in there too, right? That's important, because it's 3.8 years after 1994 when the number of prosecutions will double from the 6,100 that it was initial, the initial amount. If you had put 6,100 in here, right, then you would have had to put double that over here, and that's okay, right? Just make sure you know that that's what you would have to do. So you would have 12,200 on this side, and then you still divide, and you end up with the same exact formula. So it doesn't change anything. All right, and let's take a look at the last example here. It says the cost of a stamp in 1962 was 4 cents. In 2020, the cost of a stamp is 55 cents. Assuming the price of a stamp grows exponentially, determine the following. So the first thing I want us to find is the growth rate. When I say the growth rate, we're talking about, we want to find K. Right, so we don't know what K is. We're going to try to find K. And to find K, we have to use what they gave us. So first off, they told us, assuming it grows exponentially. So we know we have an exponential growth formula. So I know I'm using, P of t equals P0 e to the kt. And, they didn't tell you exactly what to use as your initial starting time, so we have to pick that. So I'm going to say we use, the first value they told us about, the first time point. So we use t equals year equals 0 in 1962. In other words, t is years since 1962. And since I know that, right, that's my first point, then I can say then p sub 0 is the initial amount in 1962 would be 4 cents. And because I want to talk about this in terms of money, I'm going to put it as $0.04, just because eventually this will turn into dollars, and you don't want to use cents for everything, right? You don't want to be talking about hundreds of cents. You want to talk about dollars. So we're going to use t equals 0 in 1962, right? The earliest time that they told us about, and then that tells us that P0 equals 0.04. Now you don't have to do it this way, but it'll make it easier to work with if you do. So t is years since 1962. And then we say in 2020, the cost of a stamp is 55 cents. So that's a point that we know, and we're going to use that to help us find K. So here's our general formula, right? So we use t equals 0 in 1962, then P0 equals 0.04. So I know I have this formula, P of t equals, we've got 0.04 e to the kt. And now what they're doing by telling us that in 2020 the cost of a stamp is 55 cents is they're actually giving us another point in here that we can use so we can solve for K. So when t equals, or I guess I should say really, when we have 2020, t equals, right, 2020 minus 1962, which would be, let's take a look, 2020 minus 1962, I get 58, so it equals 58, so that's 58 years. So at 58 years, then we know we have the 0.58 comma, whatever the cost was, would be 0.55 cents. So it's actually giving you a point that you can sub in, right? And we're going to use this as the t value and then the corresponding, p of t value, the y value. So in other words, right, I could say p of 58 equals 0.55. And that means my formula becomes this, right? So to solve this for k, I need this other point to sub in. So I end up with 0.55, because I'm looking at this very specific point in time now, right? The P of 58 is 0.55, that's the left side, right? That's the price of a stamp in 2020. It's equal to 0.04 times e to the k times t. T, remember, this is specific now. 55 cents was when the time was 58 years, so k times 58. And then we want to solve this, kind of like what we did earlier, right? So the second point you have, the one at the later point in time, is an initial condition for you to use to help you find that k. We're going to use that a lot when we talk about decay type problems. But once you're here, right, we're going to say let's divide both sides of this by 0.04 to isolate the exponential so we can solve. So I got 0.55 over 0.04 is equal to e to the k times 58 is the same as saying 58k. And then to solve this, we take natural log of each side. I'd leave this as a decimal for now. So natural log of 0.55 over 0.04 is equal to the natural log of e to the 58k. And remembering, natural log of e to a power is just the power because the bases match. So natural log of 0.55 over 0.04 is equal to just 58k. And then to solve this, we divide both sides by 58. Divide by 58. And we're going to approximate k here. And if I do this, let's be careful with how you type it in. It's natural log of that division, so it's ln, and then in the parentheses it's 0.55 divided by 0.04. Don't take the natural log of each part of that. It's the natural log of that whole thing. And then that, in parentheses, divided by 58. If your calculator does not display everything on the screen like I did, you want to do the division first, then take the log, and then divide by the 58. And this comes out to approximately, we've got 0.045, I'll round that to 2. So 0.0452. And this is k's approximation. Now, what was k? K was going to be the growth rate. We typically will talk about this as a percent. So if I wanted this as a percent, remember, multiply by 100 moves it 2 over. So 4.52%, right, per year is the growth rate. Right, is the growth rate in the price of a stamp per year. Right, so 4.52% per year, maybe I'll just write it here, is the growth rate in price for a stamp. Just so you remember what we're talking about, right? So the growth rate in price for the stamp is going up by 4.52% per year. Now, given this, right, we found k. Now we can use this to substitute into our formula here, right? This is our general formula. We could actually substitute into it, and now we can use this formula for any time t after 1962. So our general formula for this next part, approximate the cost of a stamp in the year 2032. Well, our general formula, P of t, is equal to 0.04 e to the, remember this is 0.0452 times t. T is our variable. In this specific case, in 2032, t is equal to 2032 minus 1962, right? That's how we're really figuring out what to substitute in. So what's that give us? 70. Let's just make sure 2032 minus 1962. That's 70 years. So what I'm really asked to find here is we're trying to find P of 70. So that equals 0.04 e to the 0.0452 times 70. And we can just evaluate this. If your calculator does not display it on the screen, remember, multiply the exponents first, then take the exponential, then multiply by 0.04. If your calculator does show it on the screen, you could multiply it right out. 0.04 times e to the 0.052 times 70 power. Make sure that you have parentheses around that whole exponent on e, because it needs to all be raised to that power. And we're left with, we've got 0.9466. 0.9466, remember what we're finding here. This is the price of a stamp. right? So 0.94, the 6 will round that 4 up, so 0.95. So what we're really finding is that the price of a stamp, right, is 95 cents. All right. So price of stamp in 2032. Now, remember, this model is an approximation. We don't actually know if it'll be that, right? Essentially, if it doesn't grow exponentially, it might not get to that value. The other thing to think about here is that, there's other outside factors. Models typically are good for a limited amount of time, and then things change. So, when you actually use anything to model, typically it's over a certain time interval. Could this be the price of a stamp in 2032? Sure. I mean, it could be, and our model says that that's what it's likely to be if this was growing exponentially. But it doesn't mean it has to be. And, you have to make sure that you understand that, the model is just a way of approximating. It's not a way of actually knowing.